Okay, now let's see this question. This question came in GATE 2014 for 2 marks. The question is, the number of distinct minimum spanning trees for the weighted graph given below is what? Okay, so they are talking about minimum spanning trees and they are talking about how many distinct minimum spanning trees can be possible. And here obviously there is a repetition in the weights of edges. See, only ones and twos are there. There are many edges, but only they all consist of either one or two, and that's why since all the values are not unique, so there is a possibility of distinct minimum spanning trees. Let's see. Now let's approach it using Kruskal's algorithm. In Kruskal's algorithm, whatever the edge weights are there, they are sorted, and then we take the edges starting from the beginning, that is the smallest shortest one, and then we are going to keep on adding those edges till we don't form a loop. Okay, so let's start. So here we are seeing that only ones and twos are there, so definitely firstly we'll pick all ones if possible. Okay, so one is here, 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 here and here. Okay, so there are 5 ones. Firstly let's talk about that uh, adding that is going to make any problem or not. So we can clearly see that if we simply, let's say, add, let's say, this one. So this is, let's say, the first chosen edge for MST. This works fine. Now we have to keep on firstly considering the edge weight 1. So here this also we can pick. Okay, so this is okay. Now we can add this one also. This is also having edge weight 1, and we can clearly add this one also because there is no problem, no loops are formed as of now. Okay, so 4 we have added. Now what about this one also can be added. So actually we have exhausted all the edge weights with value 1, and we have not formed any loop, so no issues as of now. Now let's come to 2. Now firstly let's see that how many nodes are there. Say 3 to 5, 5 and 3, 8 and 1, 9. Okay, so 9 nodes are there overall in this graph, so they are going to be 9 minus 1 is equal to 8. So 8 different edges are going to be there in our spanning tree, minimum spanning tree. In fact, in any tree, any spanning tree, there will be 8 edges, but we are talking about minimum spanning tree, which is also a spanning tree. So there will be 8 edges. Now how many edges we have covered as of now? 2 to 4, 1, 5. 5 edges are there. Obviously there are going to be 3 more edges which are going to be added to this this graph in order to make it a spanning tree. So see, this and this, they are basically separate, in fact, connected components. So if we don't include this in the graph, the end graph will not be a spanning tree at all. So there is no way we cannot have this edge, so definitely we are going to have this edge in our final spanning tree. So now we have come back to 6 edges. Okay, so 3, 2, 5, 1, 6. Now we have to add 2 more edges, and in fact all the edges are covered, but basically the graph is still not connected. See, actually this is a separate component and this is a separate component and this is a separate connected component. So what happens is that in order to join these 3 components, we already have 6 edges and we need 2 more edges in order to join these connected components, and that is going to happen like this. So let's say here we have to connect this and this, and it does not matter whether we connect it by this edge or this edge, but we cannot use both of them because then there will be a loop. So only one of these 2 edges are there. One of these 2 edges are allowed, and we have 2 options because both of them have the same edge weight. So we have 2 options, either we choose this edge or we choose this edge. So basically there are 2 options here. There are 2 different options in which we can choose. Let's put it aside and let's come back here. Here also we can see that actually here there are three options. Either we can choose this edge or this edge or this edge, and it does not matter. If we choose any of these three edges, but on only one of these three edges, then we are going to connect this component with this component, and then we will get a spanning tree, right? And that will be a smallest one, because we are going to add edge weight 2, which is the only possibility in this case. So here there are three options: one option this, one option this, and one option this. So there are three different options here, and two different options here. So overall they are going to be 3 into 2 is equal to 6 ways in which distinct minimum spanning trees can be found. Each one of them will be a spanning tree, right? Will be a minimum spanning tree, right? But that will be a distinct spanning tree, minimum spanning tree. See, if let's say we have used this edge, okay, so there is an option, so let's make it a different color. So let's say we have used this edge and this edge, then that is one spanning tree, okay, and it is a minimum spanning tree, of course, but it is a distinct one, because another one, if we don't choose this and rather choose this, then that will be a distinct one. So for each one of the possibility here, there are two ways, and there are three possibilities here, right? So 3 into 2, there are 6 different ways in which distinct spanning trees can be formed, okay? So the number of distinct spanning trees for this graph, weighted graph, is basically 6. So 6 is the answer.